like to thank Giovanni for giving me the opportunity to give this talk. And what I'd like to do is briefly talk about some aspects of chiral spintronics, and in particular, talk about anti-Skermions, block and nail Skermions, and briefly mention also this racetrack memory that I'm very interested in. First, I just wanted to acknowledge my collaborators here at the Max Planck in my institute, my students and postdocs, and I also wanted to acknowledge in particular Claudia Felser and her group members who've made most of the single crystal materials that I'm going to discuss today. And I wanted also to acknowledge Birger Goebel and Ingrid Mattig from the university here in Halle, and Daniel Loss and his collaborators in Basel for their contributions to some of the theoretical understanding of these Skermion objects that we see. I want to put this in context and briefly discuss racetrack memory. This is a memory that's dear to my heart that I proposed. I can't believe it. It's almost 20 years ago. The basic concept is very simple. As shown in this cartoon, you have a magnetic nanowire, a homogeneous magnetic material, and you create magnetic regions in this material, shown here as blue and red, and information can be encoded in the boundaries between these regions in the form of domain walls. And the basic concept, the basic principle, is that by passing current pulses through this wire, we can move synchronously these domain walls backwards and forwards to reading and writing devices that are built into this wire. If we can succeed in doing this, then we could build a three-dimensional storage class memory would have the capacity of a magnetic disk drive. So when I first proposed this, actually it was in 2002, then at that time, it had not yet been demonstrated that currents could manipulate domain walls in this way. And we first demonstrated that in 2008 in a paper we published in Science. And in that paper, we showed in a racetrack form from a soft nickel iron material where the magnetization is in plane, then by passing a current into nickel iron, it was known that the current becomes spin polarized, significantly spin polarized through spin-dependent scattering. Then current then, in principle, can deliver angular momentum to the domain walls and can move them. And that's what we demonstrated. We demonstrated we could move a series of domain walls backwards and forwards. And so we could, that was the basic principle of racetrack memory. However, soft magnetic materials, the domain walls are both very large and are quite elastic. So it's not really suitable for application. So later on, by switching to a material, again, still using volume spin transfer torque, but a material made from ultra-thin layers of cobalt and nickel, which becomes perpendicular. Again, we showed we can move domain walls roughly the same velocity as in permalloy in the same direction by volume spin transfer torques. Now later on, we and others showed actually there's an even more interesting way of manipulating domain walls, and that's through spin orbit torques, where shown on the left-hand side, you can see this yellow layer, which is platinum. And when you pass current into platinum, as you all know, through the spin Hall effect, you can generate chiral spin currents, pure spin currents, that can diffuse into a racetrack grown on top. And then this racetrack layer, the domain walls, can be moved by spin orbit torques related to these spin currents. And now, of course, what's happened over the last few years is that these spin Hall angles in these heavy metals have found to be much larger than was originally anticipated. And in platinum, we demonstrated that after taking into account the transparency of the interface between platinum and, let's say, cobalt, the spin Hall angle is about 20%. However, recently we've discovered some new alloys, compound alloys, in which we've seen through potential scattering, not a topological effect, we've seen conventional scattering effects, and we can increase the spin Hall angle to more than 1. And I think this is a very remarkable effect. Nevertheless, again, in magnetic materials, in order to create interesting technologies on the nanoscale, most importantly, you have to control the long-range dipole fields. And so I propose we could build a racetrack from a synthetic antiferromagnet, which is something that I'd proposed originally for spin valve sensors many years ago, and actually was used in the very first spin valve sensors by IBM. The synthetic antiferromagnetic here is that we create two identical racetrack layers, magnetic layers, one on top of each other, coupled antiferromagnetically through an ultra-thin ruthenium layer. Again, this discovery I made many, many years ago. And then you can eliminate the total dipole field. Well, when we did this, it turns out we discovered that that anti-ferromagnetic exchange field between ruthenium coupling the upper racetrack to the lower racetrack anti-ferromagnetically, that gives rise to an additional, what we call a giant exchange torque, which is even more efficient than these spin orbit torques. And then the domain walls move 5 times faster. So for example, take the racetrack, you change that ruthenium layer by 2 angstroms. So the thickness changes from anti-ferromagnetic coupling to ferromagnetic, the domain walls will move 5 times more slowly. So that's amazing. It's exactly the same structure. So it's a really interesting effect. Now, I don't want to talk so much about racetrack, just remind you that these are the essential ingredients. First of all, we have to make the racetrack. We could make it from bulk materials. We make it here from ultra-thin layers of cobalt and nickel, each one only just a few angstroms thick. This gives rise to strong perpendicular magnetic anisotropy. And by building this cobalt-nickel-cobalt multilayer on an underlayer, which has significant spin-orbit coupling, it turns out that the interface between this orange layer, let's say it's platinum, and the cobalt layer shown here as green, gives rise to this Dirichlet-Skermions vector exchange. And that causes the domain walls in the perpendicularly magnetized cobalt-nickel-cobalt sandwich to be chiral and nail-like. And so if we move along this racetrack, as shown in this rather bad cartoon I've drawn, the red domain pointing up and the blue domain pointing down, you can see this green arrow shows you that the magnetization rotates from up to down in a plane perpendicular to the domain wall. And when the magnetization rotates from the blue domain, from down to up the red domain, then you see this little green arrow is rotated by 180 degrees because the domain wall has fundamentally a chiral nail structure. And it's super important. Without this chirality, the domain walls will not move in the same direction. In the presence now of the spin-orbit torque, which is derived from that same platinum layer in which we convert via the spin Hall effect the charge current into the spin current, which then diffuses into the magnetic layer. And then, of course, I also mentioned we need to build this synthetic antiferromagnet to eliminate the dipole fields. So first, then most of our experiments to date have been using Kerr microscopy, and in the top you can see a simple cobalt-nickel-cobalt racetrack. It's just 1 nanometer thick, grown on platinum, and the domain walls move by nanosecond long current pulses at speeds of up to approximately 300 meters per second. Underneath you can see a synthetic antiferromagnetic racetrack, basically an identical structure in which on top we've built another cobalt-nickel-cobalt racetrack coupled through the yellow ruthenium layer antiferromagnetically, so there's no net magnetization from this structure. The domain walls move 5 times faster, and of course in the Kerr microscope the signal is much weaker because there's no net magnetization. So very interestingly then, racetrack is derived from the interplay of these 4 spin orbit derived phenomena: anisotropy, I didn't discuss proximity-induced magnetization, chiral domain walls, and spin currents from spin Hall effect. Now it has been proposed that instead of using these chiral domain walls, which are just a few nanometers wide, one could instead imagine a racetrack memory in which you use Skermions as basically the information storage element. So I want to briefly discuss some of our own work on Skermions. First of all, just let me remind you, what is a Skermion? It typically is a circular object, a material that otherwise wants to be, the magnetization wants to be aligned in a particular direction. It turns out that for some magnetic field and temperature regimes, you see instead a ground state that consists of an hexagonal, typically hexagonal array of these circular objects. What the circular object in the interior, the magnetization is inverted compared to the exterior. On the right-hand side, you can see a nail-like Skermion, and in this case, just like our chiral nail domain walls stabilized by an interface Dirichlet-Skermions exchange vector, here it's typically a volume DMI vector, and depending upon the symmetry of the crystal lattice, this gives rise to a nail-like wall, as shown on the right-hand side, where the magnetization rotates from up the outside to down on the inside along the radius, where that's what happens, just like the chiral domain walls in racetrack. On the other hand, a block Skermion on the left-hand side, it looks similar, but here the magnetization rotates from outside up to inside down in a plane which is perpendicular to the radius. And this is the type of Skermion that was originally first observed by Christian Fleiderer in manganese silicon, and he originally did that by neutron scattering, and subsequently was observed in iron germanium by Takura and his collaborators by using Lorentz transmission electron microscopy. And I just wanted to point out, I'm going to briefly discuss at the beginning our observation of an anti-Skermion. An anti-Skermion has a more complex boundary structure that consists of both nail walls and block walls. And as you rotate around the circumference, there are two directions, if you like, four directions in which you see block walls, and another four directions with nail walls. And the chirality changes also as you rotate or go around this circumference. So it has a very complex structure that was predicted theoretically before our work. We're going to use Lorentz transmission electron microscopy. Let me just remind you briefly, you have to then take a very thin layer or lamellar of this material, which is electron transparent. You pass an electron beam typically perpendicular to the lamellar, and the electrons, as they pass through this magnetic material, will suffer a Lorentz deflection, so they're sensitive to the in-plane components of the magnetization in this case. What we can do is we can then basically use micromagnetic simulations to calculate the structure that we expect, depending upon the crystal symmetry and the symmetry imposed on the Dzerzhinsky-Murray exchange vector. So a student of mine, Jiangping Ma, has basically introduced all the symmetries that are possible and has calculated all the possible spin textures that you could imagine based on micromagnetic simulations. Then we can carry out standard calculations of the image we expect to see in the Lorentz microscope. Just to remind you then, on the left-hand side, the block Skermions look like in the Lorentz image, these white dots. And so that's very nice, and that was originally observed by Takura and his group. On the right-hand side, the nail Skermion has a different form, and in fact, if the electron beam is perpendicular to the lamina, there's actually no deflection. Nothing you see, and this is because the beam is deflected around the circumference of the object. However, if you rotate the lamella with respect to the electron beam, then you see something. I'm going to discuss that later. The anti-Skermion, we calculated we should observe this cloverleaf-like pattern in the middle. You see these two white dots of increased electron intensity and two black dots of decreased electron intensity in the Lorentz image. So now, I first want to briefly discuss Heusler material, because this has a symmetry that should sustain an anti-Skermion. And this is work, as I said, we carried out with Claudia Felser and her group. And they had found several years earlier that with Jürgen Kübler, they calculated, or they had some measurements that suggested that in these systems, manganese 2 platinum tin, for example, manganese 2 rhodium tin, that the structure at low temperatures, they thought, was no longer collinear. So the basic Heusler compound is a cubic system for interpenetrating lattices, but when you introduce magnetism, this gives rise to a tetragonal distortion, and there's a strong unidirectional anisotropy. And so basically the structure shown here consists of alternating layers of manganese tin and manganese platinum. This is an inverse tetragonal Heusler structure. And then Jürgen Kübler calculated that at low temperatures, he anticipated the structure, which is ferrimagnet, would become non-collinear. We did some Hall measurements that suggested evidence for a topological Hall effect at low temperatures. Well, took us considerable effort, but first we had to modify our microscope here in Halle So we could do Lorentz microscopy, that took a year. And then we had to make lamella using focused ion beam milling. And then we finally saw this object, which I think hopefully you can see in A here, which consists of this clover leaf structure, just as we had simulated in our simulations. And basically these anti-Skermions, just like the block Skermions and the nail Skermions, appear as arrays. And you can see then in C at room temperature, you can see an array of these anti-Skermion objects. Now we can, in Lorentz microscope, we can vary the temperature and magnetic field. And as we increase the field, we can eventually see at room temperature that we observe basically the anti-Skermions disappear and we see a uniform state. What I want to do briefly is discuss the dependence of the phase diagram and the size of these anti-Skermions on the thickness of this lamella through which the electron beam is transmitted. So to do this, we again make a lemma, we cut a lamella from a single crystal by focused ion beam milling, typically with gallium ion beam, in which the thickness varies from one end to the other. You can see this in the scanning electron microscopy image in here. And then down below, we've basically taken 3 regions which have different thicknesses, here only varying from 160 nanometers to 250 nanometers, and this ABC. And what you can see there is, if we, on the left-hand side, the images are in the saturated magnetic field. And as we reduce the magnetic field, then depending upon the thickness, you see when the region is thicker, the anti-Skermions are more stable. But anyway, as we reduce the field, you start to see the arrays of anti-Skermions, and then at the lowest fields, you actually see a different structure. And you can see this on the right-hand side. You see these alternating white and black lines, and these correspond to a sinusoidal variation of the in-plane magnetization. It corresponds to a helical or a cycloidal-like structure. And these structures, these helices, we see directed only along 2 in-plane perpendicular directions. And these are the directions in the crystal lattice which stabilize block-like walls. And it turns out they have a lower energy than the nail-like walls, which is why these helical structures appear along these 2 directions. Now, the spacing between these white lines corresponds to the period of this helix. And I want to briefly discuss that. So here you can see on the right-hand side an image, a Lorentz image of this wedge whose thickness is increasing from the right to the left. And I think you can just visually see that the white lines are closer together on the right-hand side than on the left-hand side in the thicker region of the sample. And quite surprisingly, even though the thickness of this lamella is only varying from 40 to 160 nanometers, the period of this helix doubles in that thickness range. And again, you see, as you can see very clearly, these helices oriented along 2 perpendicular directions. Now it turns out then, to look at thicker lamella, we can no longer use Lorentz microscopy because the lamella is no longer sufficiently electron transparent. So instead, we switch to variable temperature magnetic force microscopy, which now senses the out-of-plane component of magnetization. So now we see on the left-hand side, you see a beautiful image. And if we take a line profile, we can see that we see a sinusoidal variation of the outer-plane component of the magnetization. And again, we can take then the period, and the period of this helix increases monotonically all the way up to here, 1.6 micron thick lamella. And here we've gone a little bit further. We have a rectangular lamella, which is thickness increasing from left to right up to 4 microns. And in this case, we can, by changing the magnetic field as direction, we can set the helix either so that the helical direction is perpendicular to this rectangularly shaped lamella, or rather along the length of this rectangle, or we can set it so that we have both types of helical domains present. And again, you can see very clearly they're oriented along two perpendicular directions. And I think, of course, you can see from these magnetic force microscopy images that the period is much smaller on the left-hand side in the thinner part of the lamella than on the right-hand side. And you can see on the right-hand side then how the period of the helix increases monotonically up to a thickness of 4 microns. Now again, by changing the magnetic field, we can stabilize anti-Skermions. And these anti-Skermions then look like just dots, because now we're just detecting the out-of-plane Z component. And it's visually very obvious that the size changes from a smaller diameter on the left to the right. And if we plot the diameter of the Skermions versus thickness, we see a monotonic increase all the way up to 4 microns. And it turns out there's a one-to-one correspondence between the diameter of the anti-Skermion and the period of the helix. Now these anti-Skermions then become so large that we can now detect them optically using curve microscopy. I don't want to discuss this in too much detail because I don't really have enough time, but I just wanted to point out then that we can carry out micromagnetic simulations where we include, as I said, the Dzyaloshinskii-Maria vector, and we can compare the standard B20 structure, which is a cubic system where the vector has equal components in X, Y, Z. And what you find from micromagnetic simulations is that as you increase the thickness, here it increases from top to bottom, and as a function of increasing magnetic field, you see a stability window for Skermions, which is much smaller than for anti-Skermions. So for Skermions, as you increase the thickness, then they disappear, whereas for anti-Skermions, there's no sensitivity to the thickness of this structure. So they're basically, and the reason for this is that in the anti-Skermion system, which is a lower system with D2D symmetry, there's no component of the DMI, the Dzyaloshinskii-Maria vector, along the tetragonal axis of this Heusler material. So they basically can remain stable to large thicknesses, unlike the Skermions in the B20 system. Now, what we discovered more recently was that in the same Heusler compound, here it's a manganese 2 platinum tin derived material, then by changing the temperature and field, then Yaganov, Jane, one of my PhD students, discovered that he could see a totally distinct topological object. And we called this an elliptical block Skermion. And I think you can see this very easily here in these images. You see an array of these elliptical objects, which are basically arise from, as you can see here, these helices. And the direction, the long axis of this elliptical block Skermion, again, is along the direction which favors the helical structure, these two directions in plane. This was the first observation of two topological spin textures in the same material. I think around about the same time, or Takura's group, who actually duplicated our anti-Skermion material, found a similar result. So here's very beautiful. You can see a Lorentz image where we see these two two elliptical block Skermions in perpendicular directions. And what it means is these objects only have block walls, unlike the anti-Skermion, which has this complex block-nail type structure. This is what we see. Very, very beautiful work from Yaganov. Now, what we find then is that depending upon temperature, we can stabilize rather the elliptical Skermions at low temperature and the anti-Skermions at high temperature. And the reason for this is that at lower temperatures, we believe we have a higher magnetization and a stronger role of the dipole fields. And it turns out in this system, because of this low symmetry system, dipole-dipole interactions play a very important role. I didn't discuss that, but that actually is responsible for the size dependence of these objects. As you change the thickness of the lamella, then the role of the dipole-dipole interactions change. In principle, the size of these anti-Skermions should be much larger in very, very thin layers. This is one of the reasons why we're trying to make, by thin film techniques, layers of Heuslers, which we need 1 or 2 unit cell thick structures. Anyway, what we show here is that at low temperatures, then the dipole-dipole interaction favors the block Skermions, but they're distorted because of the DMI interaction. And at high temperatures, the anti-Skermions are favored, but they can become distorted to these square-shaped objects because the block component, the block regions of the boundary are favored by dipole-dipole interactions. Then we tend to see these, if you see on the right-hand side, a square array of square-like objects, so this is very amazing. We can really, by subtly changing the DMI and the dipole interactions through temperature and field, we can see a whole variety of objects of different shapes and sizes in this material. I'm not going to discuss this. Basically, we're also looking at sort of racetracks. We can make narrow tracks from this single crystal material, in which we can see individual rows of anti-Skermions. And we're using these to look for current-induced motion. It turns out that just by passing current through this material, these anti-Skermions do not move, although we see the temperature gradients can move them. And then this is here, we just show, we can see 1 row of anti-Skermions or 2 rows of anti-Skermions, but I don't want to discuss that. And we potentially could make racetracks by using 2 distinct topological objects, for one as a 0 and one as a 1. And I want to just briefly then, I'm running out of time, is to say that, well, we've discovered recently a very interesting observation that at the very edges of these lamella, we actually see another object. It's not so easy to see here, but what we see at the edges, we actually see a fractional anti-Skermion or a fractional block Skermion. And so with the help of Daniel Loss and his team in Basel, they've carried out micromagnetic simulations that show, indeed, that at the edges of these lamella, you can stabilize these fractional objects, which effectively only exist at the boundary because in the interior, you have this array of anti-Skermions or block Skermions. So this is very interesting. It's really, they only exist at the edges because of the interior structure. It's the first time that these have been observed, as far as we know, and that the winding number is not integer, it can be varied. So these are really fractional objects. And we just want to make a comparison between the B20 systems where these have not been observed and our systems, these D2D systems. And we believe it because in the B20 systems, as I said, you have a twisting of the magnetization in all directions, and potentially one can't see them because they're essentially averaged out over the thickness of the lamella, whereas in the D2D systems, this is not the case. We get very straight tubes. This is from micromagnetic simulations. Of course, we're looking for thin films, and I'm again not going to discuss this in detail. It's some nice work where we can see we can grow thin films of Heuslers. They're relatively thick, 13 nanometers thick, and we see from magnetic force microscopy evidence for spin textures which appear to look like anti-Skermions, in the sense that the temperature field phase diagram that we observe on the right-hand side is basically identical to a single crystal bulk material in which we've looked also and seen also these objects. What's interesting is we can, by using the magnetic field from the magnetic tip in the magnetic force microscope, we can basically eliminate, erase these objects as shown on the right-hand side by bringing the tip close enough together. And we can also write arrays of these objects by using, again, the magnetic field from the tip. So this means that we can write and erase, and we can't yet manipulate them with current. They also don't move in this system, but we eventually expect to be able to move them by spin orbit torques from spin currents derived from neighboring layers. Now, if there's any time, I want to briefly mention, if I don't have time, 2 other systems. One, I just wanted to point out that platinum, manganese, gallium is a very nice layered system. Platinum, strong spin orbit coupling, it turns out for many, many years, this system was believed to be centrosymmetric. So we were quite surprised when we saw nail Skermions in the system. And then Holger Meyerheim in my group carried out really detailed X-ray diffraction study and showed that the structure that people had believed for 20 or 30 years was actually not correct. And this system actually is a non-centrosymmetric system with a layered structure shown here of manganese, and the gallium platinum layer is actually slightly distorted. So it's actually a layered structure. And this is the reason why in this system we can observe Skermions. The symmetry requires that they be nail Skermions. And as I mentioned in the very beginning, a nail Skermion is invisible in Lorentz microscopy when the electron beam is perpendicular to the layered structure. But by tilting, and these are images taken by tilting by -9 degrees on the left or by +9 degrees on the right. And I think if you look very closely, you can see this object now looks like a white-black object. And on the right-hand side, it's black-white. That's because we've tilted it to opposite directions. And then in the Lorentz image, it should be reversed. And that's what we observe. So it's clear that it's a nail Skermion. And then what we find, again, by looking at the thickness dependencies, we can see that the size of these objects also increases with thickness. And this is shown summarized on the right-hand side. You see for very thin layers, they're below 100 nanometers. For 3 micron thick layers, they're about 500 nanometers in size. So this is a remarkable material. It's the first metal system showing nail Skermions. It's at much higher temperatures. Nail Skermions had only been seen at low temperatures in some complex insulating objects. And also we see very beautiful size dependence, which has only been observed otherwise in this Heusler material. And then I finally wanted to just, if there's one moment, to say recently we've been looking into a lot of 2D ferromagnets, and several groups have published work on the observation of Skermions in this iron 3 germanium tellurium 2, which normally should be centrosymmetric. So several groups have said, oh, one of the surfaces must be oxidized, the breaks of symmetry. Seems unlikely because typically people are looking at very thick, they're not looking at monolayers, they're relatively thick layers. And what we've discovered, again, with Holger Meyerheim's help, we believe that the structure is not centrosymmetric, but actually due to ion vacancies, it's non-centrosymmetric. And if you look on the left-hand side of the structure, you can see this, the red is tellurium, the green is iron, and germanium is in pink. You have the unit cell consists of these 2 layers offset so it's centrosymmetric. And what we have discovered, well, Holger's discovered, is that the concentration of ion vacancies in one layer is distinct from the other layer. And this is shown on the right-hand side. This is the so-called goodness of fit curve as we change the occupancy of these 2 sites. I don't know if you can see them, site 6, which is an ion site, and site 5. And the best fit, which is a very good fit, is obtained for different amounts of iron in these 2 sites. There's also some iron in the van der Waals scab. So this 2D materials are really interesting because it turns out that structures are much more complicated typically than is believed. This one is non-centrosymmetric, we believe, due to this different occupancy of these ion sites. And this leads us to see in this system nail Skermions, and again, we find that their size varies significantly as a function of thickness. So on the left-hand side, you can see these beautiful images. Now you'll recognize these are magnetic force microscopy images. As we increase from the top now to the bottom, the thickness going from up to 2 microns here. And then you can see a big thickness range. So I think we've now observed this strong size dependence in 4 distinct systems, and I'm not sure that others have yet observed this phenomenon. So now I want to, sorry for going over time, I want to just summarize. Racetrack memory is a concept of synchronously moving with current pulses, a series of domain walls that represent zeros and ones. And although I've only shown you micron wide racetracks, we're now making racetracks 50 nanometers wide. Turns out the domain wall velocities are the same. So there's no pinning of the domain walls at the edges, and we can reliably move these domain walls to positions of a few, spaced by a few tens of nanometers. And I've discussed anti-Skermions and a second topological object, elliptical block Skermions in tetragonal inverse Heusslers, and showed you how the size varies with increasing thickness of the lamellar. This is a consequence of dipole fields. And we've also seen these fractional spin textures for the first time at the edges. And finally, I just briefly mentioned two other systems in which we've observed nail Skermions in metallic systems. And this is the 2D system, iron 3 germanium tellurium 2, and platinum manganese gallium, which was the first metallic system in which nail Skermions were observed. And so I want to thank you for your attention. And I also want to thank all my collaborators that I had mentioned in the first part of my talk. So thank you very much.